Hello? Yep. Okay, good. So, hello. Hey. So this is a talk about an effect system, which is a type system extension that I'm going to use to reason about side effectful behaviors of programs. But it's not just to reason to a predefined set of side effects that the language designer has come up with, but rather to allow you to reason over user-definable side effects, which in object-oriented languages are usually represented by defining a method. You'll notice a slight square here. That should be epsilon, so it should read CallE. Yeah. Okay, so basically the main observation I made was that in object-oriented languages, if you want to do I/O, you will call a method to say print, right? Or read, or append to a file, etc. Right? And so these are just all in the library, right? They're often not defined by the semantics of the language. And users can write their own versions. So if you might want to implement a print method, it might append to the standard output file, right? But that is often an implementation detail. And so we still want to be able to reason about printing as something different from appending to a file, and printing, of course, is less powerful because you only print to one file and not to any arbitrary file. So the way an effect system works is that when you've got an expression and you type check it, you compute the effects that it has, which is literally just the list of methods you're calling. So here it's just console.println and string.append, right? And of course it computes the return type like you would see in any normal type system, right? Now that is useful because we can then abstract that into a method, give the method a signature, which will then restrict what the effect of its body can be, right? And then we only need to look at the method signature to see what it could do, right? And we don't need to look at the body. So the way this works is you attach an effect annotation to the method, and you give an effect list, right? Remember that effects are just method calls, although later on I will show you some additional effects. Right? So we can put this thing in a method, and we can declare its effect as append.println. And that works trivially because that is exactly the effect of this expression. However, that obviously exposes the implementation detail here, and so if you change something here, this annotation will then, might be different. Now, and of course we've got an append method, which is not really an effectful operation that you're unlikely to care about. So the semantics of this effect annotation shouldn't be interpreted as the effect of the body is exactly this, but the effect of the body is at most this, which means that the body of the expression can at most print a line and append to a string, right? And we can consider, and I will show you later on, how we can declare this method so that it's unaffectable, and so that we don't need to care about it from the point of effect annotations, right? And you'll also notice this print line method, which is a bit specific, right? What we're really just doing is printing, right? Does the caller of the method need to know that we're going to terminate it with a new line? Maybe they do, maybe they don't. But if they don't need to know that, right, and you don't want to constrain your implementation to do that, right, I will show you later on how that you can just write console.print here, right? And this will give you a guarantee without having to look at the body, right, that's not going to read from the console or do network or something else that might be defined in your libraries, right? So the way this is done by the type system, right, is by using the sub-effect relation, right? What it will do is that it will check that the effects of the body of the method, which here is E prime, right, are all sub-effects of the declared effect, which is the epsilon here. The delta is just the context that will, in the formalism in the paper where I've written all the typing rules, this context just contains generic type parameters, which I will discuss later. Right? So here are the first few rules, right, of this relation. This one means that it's reflexive when you treat the list as sets. So you can duplicate effects and reorder them, it doesn't matter. Right? So basically this should be considered an effect even though you would write it down, a set, sorry, even though you would write it down as a list, you know, with commas in between, of course. And this shows the sub-effect relation is transitive, and the empty effect list is the least powerful effect. So if your method body literally doesn't call any methods, it trivially satisfies its effect annotation. This shows that adding to lists of effects will preserve the sub-effecting relation. And so altogether, right, these four rules imply that, right, well, on their own, these four rules are equivalent to saying that a subset is always a sub-effect. And so if there's less effects here, right, then it's clearly less powerful than there. But there will be other rules that I will show you, which is why, right, that integrate with these, which is why I've split it up into 4 rules instead of just giving you a simple subset rule. Right? And so with this, we can go back to our hello method and just add an extra method. Here's the effect annotation, console.read. It doesn't actually, but that's okay. Right? This is useful because later on you might want to change the implementation and just add a console.read here, and whoever's relying on this annotation is going to still be happy. Right. Now, the main novel thing about my sub-effect relation, as opposed to many others you will find in the literature, right, is this particular rule. What this says is that a method is always a sub-effect of whatever that method's effect annotation is. Now, basically, this means that if you've got a method, say that my print line method, right, that's declaring its effect as print, then calling print line is at most as powerful as calling print, because that's all that print line itself can do, right? And this is useful because this means you can just put print in your method annotation and not print line, which I will show you in more detail now. Right? Now we can go back to our string append method, and we can declare it with an empty list. Right? Assuming here that it only calls other methods with an empty list here, or doesn't actually call any methods. Perhaps it just does a constructor call and it creates a console. Who knows how this is implemented. Now, what this empty list is make that this rule trivially applies. Because the empty list, right, will be here, and everything, whoa, what have I done? Oh, right, yes. Right? The empty list will be here, and so we've got string.append is at most as powerful as the empty list. And the empty list is the least powerful effect, and everyone can do empty list effects. Right? So now we can go to the console class. I'm just going to treat print as a foreign method, so we don't have a body, and same with read. Now, print has declared itself as an effect annotation, which basically disables this rule. And so applying this rule to this method name will just tell you that print is less than print, which obviously holds, based on my reflexivity rule that I showed you before. Right? This means that some other random method, say read, right, can't invoke this call. And so in the paper I've used terminology and saying that these methods here are uneffectful because I got the empty list here, or using any application of my rules, you can deduce that you could have put an empty list here. Right? But all the other methods are considered effectful, which are the ones we want to reason about. So in our print line method, it's got an effect of print. It's going to, and that's what it calls, just calls print and then puts a new line at the end. And so we can go back to our hello method, and using this rule, we can annotate it with print. This works because print line, according to this rule, is a sub-effect of print, which is the effect here. And it makes sense because I could have just written this loop and these two calls of print right inside hello. And we're going to got the exact same behavior. Right? But so that gives you some flexibility here. And from the caller's point of view, right, they don't really care how hello is implemented. What they care about is what it was going to do. Right? And so here's a simple example of why that can be quite powerful. We have a file system class with an append method, right, which again mentions itself in its effect annotation. We've got a log method that calls the file system append, and it appends to this log file. And so we can have another method do something that will have the log effect. Now, assuming, of course, that this method is well typed, right, but we don't have to look at the code here, the type checker will do that for us. Right? What this means is it can call the log method. But there's no way of using my rules, right, to allow it to call the append method, right? Because the append method is strictly more powerful than log. And so it can append to the txt file because it can call this method, which will do exactly that, but it can't append to an arbitrary file. Now, of course, this requires to do such reasoning, you need to actually look at the log method and understand what it's doing or rely on its documentation. If you can't do that or don't want to trust it, right, you instead of you can still get some information, and that is that it is going to append to a file by just looking at the annotation of log, right? But it's not going to do other things like delete arbitrary files, right? So the idea is that by looking at more stuff, you can get more specific guarantees, right? But if you look at less stuff, you will get some guarantee, right, though it might not be as precise. Right? And this works great with OO, right, because we support dynamic dispatch, so that when you override a method, the method here has an effect epsilon, which is overriding one with epsilon primes, and they must satisfy this relation, right? So here's an example. We've got a UI element interface and a paint method that is just going to paint that element, and children, which will contain all the nested elements. Now we've got an annotation here that says UI set pixel. And here's an example of a class implementing that interface. Its paint method has the empty list because it's not actually doing anything, right? But it's got some children here that themselves may have paint methods. Right? Because this is the empty list, this is a sub-effect of this, and so that works. Now, if we did something else, say, tried to shut down the program here, then that is likely to fail to type check. And so you don't need to look at all the implementers of UI element to know what calling paint on a UI element can do. You know that it can do at most this, right, which will set pixels. Right? This enables us to have this extra rule, which is quite important for soundness. What it says is that a method is a sub-effect of any method it overrides. And so here we've got a paint all method that's going to has an effect UI element.paint. Internally, it can call paint on containers and all sorts of other things, right? Doesn't matter, right? Because all of those paint methods are all implementing UI element.paint. And so it can't do any more than that. And so as you can see here, we've got a call to e.paint, and we're just iterating over the children and painting them. Right? Notice how I've got a recursive call. Thanks to my rule I showed you before, the indirect callee rule, this will always type check. So you can always do recursion because you're not gaining any more power, except, of course, you are now Turing complete, and you might not terminate. Right? Notice that when you actually reduce this as an expression, this e will be replaced by a more concrete value, which will have a more concrete type, which is why we need this rule. Right? And so what soundness is basically saying, right, which I have in the paper, is that when you call a method, the behavior of what it actually calls, right, is going to be a sub-effect of what the method's annotation was, even if that method's annotation was an interface, which is not a concrete method, right, an abstract method here. Soundness will also say that any other behavior that can come from further calls will either be in this list or be under the control of one of these methods, which is where my log example showed you, right? And so your do something method had a log in the effect annotation. Calling log will do a file append operation, which is not in the effect annotation of the do something method. But that's okay because log is, and it's under the control of log. So it can only do file system.append method calls that does. So in other words, if you don't trust what's in here, it's right. If you trust what's in here, it's all good, right? It's not going to do anything more than that. If you don't, you go look at the annotation and then see if you trust that and you're happy with that. Okay, so one of the key realizations that I had that I thought was quite useful is that we don't need a separate feature for effect polymorphism, but we can just leverage over normal parametric polymorphism, which you get in lots of OO languages. So here we've got a hashable interface, which has this new star effect, right? Which, based on this rule, shows that it is the most powerful effect. So if you've got a star effect, you can do anything. Now, the reason I've done that is because there are many different use cases you might have for this interface. Many different programmers might want to implement it, and many different programmers might want to use things that are hashable. And they are all often going to have different desires as to what the effect annotation is. So this doesn't limit the interface itself, right? And same with this hash map class, right? I'm using a key.equals and key.hash, which all I've constrained is that they are hashable. So a hash map doesn't really care if there's going to be side effects when calling key.equals or key.hash. Right? Usually it's going to hope it's deterministic, right? But it need not. But I'm assuming in this case that the implementer here doesn't actually care that much about that. Now, notice how I wrote key.equals. Key is a type parameter to hash map. I haven't written hashable.equals. Right? This means that it'll only call equals methods that this key, the concrete key type you pass to, has provided. Right? This is useful because if you know what the key method, if you have more information about what the key to the hash map is going to be, the type, you get more information about what this get method can do. So here's an example where you would subtype the hashable interface, right, with random hashable, and its equals method is non-effectful, but its hash method might do some random numbers. So if you write a method f that takes a random hashable, right, and you've got a hash map with that appropriate key type, then the type system can work out that getting the element from that hash map is going to do at most random.generate. And this is because this get method is doing key.equals and key.hash, but we know that the key is a random hashable, so we know that key.equals is uneffectful, and we know that key.hash is going to do at most random.generate. And so we know that this f method is itself going to at most generate random numbers. Right? Now, there are many examples shown in the paper that show how this can be actually quite flexible and useful in reasoning. Right? So in this case, what I'm doing is I'm making a marker interface permission. I'm not expecting anyone to implement it, but they can if they want to. It won't break anything. Right? It's got a modify method with itself listed here. Right? I've got an add permission class that inherits from permission, and that will automatically get modify here with the same signature. Note that this modifier here actually refers to permission.modify, which is technically a separate method to add permission.modify, which is it's going to inherit from permission. What that means is that now we've just created out of thin air two methods, right, that can be used as in effect annotations. We've got a permission.modify method and an add permission.modify method. And the add permission.modify method is a sub-effect of permission.modify. If you call add permission.modify, right, because anything implementing add permission.modify is obviously implementing permission.modify, but vice versa doesn't hold. Right? And so if you can call any permission.modify method, you can call an add permission.modify method and something else that might not implement add permission. Right? Now we can use this to create a generic widget class. The idea here is that you can only update this elements in the sidebar if you have an appropriate permission in your effect annotation. By permission, I mean a permission.modify method. So we can make a generic over a p, which inherits from permission, and our set method, right, has the effect p.modify. It's not actually going to call p.modify, right, but it means if you have if another method has an appropriate p.modify method in its effect annotation, then it can call it, otherwise it can't. Right? And so here's an example of an add, right, in a class. It's got an update method that is going to update some widget, and it's got add permission.modify, which means that, right, any sidebars that are found or created nested inside this widget, right, that happen to have been created with an add permission here for the generic parameter, it can call the set method for. But it can't do the same for something that was created with a permission or any other subtype of permission that's not also a subtype of add permission. Right? Of course, if I had written permission.modify, right, because that's the maximum you can have here, right, that means that you can call set on any sidebar you found. And so this lets you pass a whole graph of widgets and sidebars, right, and be sure that it's only going to modify the sidebars that were created specifically to be modified by adds. Right? And the way you would do that is just new sidebar, in the angle brackets you would write add permission. Right? Another example that I've shown in the paper, right, is to help reason about leakage of information. So if we've got an SQL statement where you execute the statement, it is going to return an SQL result, which is just a simple wrapper over a string. Right? This is effectful because it's going to maybe communicate with the database, say, right, by reading and writing. Right? But it's also got the execute method here. Now, SQL result has a getter value here, right? But it's effectful, right? Even though it doesn't actually call any methods, right, what this is doing is it's restricting who can call the value method. Right? Of course, the field is private, as you can see here, so we don't have to worry about that. Right? So the only way anyone outside of SQL result can access value, the result, here is by calling this. So here's an example of an isAdult function that's taking an SQL result, which came from some query on the database, right, and it's declaring that it's going to inspect the values, right, by calling this value method. Right, and that's what it's doing, it's just checking that the age is greater than 18. And so we've got a doStuff method, which has an effect notation that's going to execute queries and call the isAdult method. But it doesn't have the SQL result.value method, so we can't directly extract out the result of any queries. But it can pass the result of queries to isAdult, which will then just check this 18. And so doStuff can't actually determine what the age of any particular user is. Right? All it can tell is whether they're over 18 or not. Right? Of course, this requires you to look at the isAdult method, right, in order to work out what's happening. And so the advantage of this here is that instead of looking at all the code and tracking how the results of execute methods are passed around, we only need to look at the code that has this effect. And then we can look at this code and see that it's not inappropriately, right, passing the result to someone who shouldn't be able to. And so this lets you sort of narrow down the search space for your program when checking that it's not leaking confidential information. Right? And so if you look at the isAdult method and you think, okay, it's okay, I don't care if anyone knows if someone's an adult. Right? Of course, if you decide, I do care who knows who's an adult, you can then further look at who's calling isAdult and say, okay, doStuff is allowed to know who's an adult, but other methods aren't. Right? Right, so another example of object creation, right, in which we've got basically a static method. I'm assuming here that there's a private constructor, so the only way to create a path is by calling this path method here, right, which will return a new path on this string, and it's effectful, and so not everyone can create a new path, right, but they can append path, which will just, go into a subfolder of the path, and there's an effectful read method that will read the file that the path refers to. Right, this is useful because we can have an untrusted method that's not allowed to create new paths, but it's allowed to read from them. And so given the list of allowed paths, it can only read the files in here. And the trusted method is going to give a list of paths, right? Because it's got a path.pass effect, it can create new paths and give it to untrusted. And so you can be sure that untrusted is only going to read things nested inside the home directory in temp. All right, this unfortunately does assume that there's no paths that untrusted can get from somewhere else, such as a global variable or if it was an instance method from its receiver. All right, but it still, right. There's another example, but I don't have time. So basically, in the paper, I have shown various extensions to what I've just presented. In particular, I show how you can support dynamic code loading and reflective invocation of methods, so dynamic invoke in Java, right, in a sound way. So you don't even need the entire program, right? You don't need to know what the entire program is in order to reason about what side effects can happen. Right? I also show effect redirection, which allows you to turn, say, a console.print method into something else, so it doesn't actually print to the console, and then have the effect system know about this. And so you now know that if I've changed the behavior of this method, right, in its context, then, variance. Yes, I just show how you can extend a variance, so you can get subtyping and subaffecting when you play around with generic parameters. If you know of wildcards in Java, it's like that. And of course, there's various future work. These extensions haven't been formalized, but I have formalized the entire type system. And I have given a sort of a soundness proof. It's mostly just a proof sketch written in English, so more formal proof would be useful, as would be various other features. Thank you.
We have a lot of time for questions.
Yes. Yep.
Can you please use the mic?
Of course. I'm wondering, so your type system or type and effect system attaches or annotates methods with effects. Are you aware of the work by Simon Gay, Vasco Vasconcelos, and others on Mongo and Beaker? They are Java-like languages where you attach effects, I'm not involved, but they call them usages, and they're protocols followed by classes.
I'm not sure. I don't think I've seen the term usages before. I've seen various effect systems where you attach effect annotations to methods, but what were these effects telling you?
But the effects in the class would tell you the admissible sequences of method calls.
Oh, okay, that sounds quite interesting.
Yes, it looks similar to effects. So the reason why I keep saying we is that I've since become part of this collective working on Mongo and Beaker, and I think what we're doing is clearly related to what you're doing.
Right, cool, thank you. I will talk.
Other questions?
Yes.
So one limitation you mentioned in the discussion about paths is that you could guarantee that you could read from, or could you go back to the slide about paths?
Yep, sure, no
You could talk about paths, you could talk about any path, not just the ones that were passed as parameters. And so I was wondering if you have looked at an extension, maybe it's sort of like dependent effects or something, where you can say, it's only these particular paths from which I can read, not all the other paths in the world.
Yes, I was thinking of something like that with a sort of abstract type, if you will. Right? And so you could put a type variable perhaps here, right? Here, that any p that's a path, and assuming that that's, and so basically because the untrusted method doesn't know exactly what p is, it can never actually use it. Does that make sense? Right? Sorry, it can use the p type, but it can't create anything of the p type because it doesn't know what it is, right? But it's in the signature here, and then the caller would specify what the p is. If that sort of makes sense?
I had in mind something more along the lines of, the actual parameter allowed paths. Only those paths are the ones that can be read.
Yeah. So you could also do I guess, path-dependent effect, if you will.
Yeah, right.
Perhaps, which is, I guess, another way of doing the same thing I was suggesting with by putting an abstract type here.
Okay. All right, thank you.
That makes sense. Any other questions? Yeah.
So there's a tension here that's common to a lot of work, right? Which is, you said, this is really good for, it's flexible and useful for doing reasoning. I think that's a phrase that I heard you say. So often that's in tension with ease of making changes to my code, right? So flexibility from the point of view of a programmer who just wants to get a thing working. So obviously that's the classic sort of, that's a big topic. But in your approach to subtyping, I was kind of worried that there was a whole new opportunity for fragile base classes here, right? Where if I didn't anticipate what effects the subclass method could have, then I've made it really, really hard to make that kind of change.
Yeah, absolutely. That's exactly the same problem you're going to get when you specify a return type of method. You specified, it must return a list, but then someone else wants to return some other collection instead. And so I don't really have an answer for that.
But it feels like the normal sort of style of method overriding is actually, it's really common to want to do that, right? I override a method to add something that is unrelated to the base class, but it's something I want to, it might involve an effect.
That's why I was, I was hoping that a base class, well, you saw my hashable interface where I had a star, right? And so anyone overriding it can put anything more concrete here.
Right.
Because the hashable interface itself doesn't care what its subclasses are doing. But if the class does care what its subclasses are doing, right, then it needs to specify. It's basically the principle of least authority. You say, I only trust my subclasses to do this. They can't do more, right? Because it doesn't know what the whole world of possible things it could do are, and they could cause havoc.
I mean, that's maybe useful. I just think it's a really big departure from object-oriented programming, so it's maybe something you could, I don't know,
I'm going to have to disagree with you on that it's a departure, because as I said, it's the same as specifying a return type. You write array list, it can only return an array list, it can't return a linked list.
Okay, let's take it offline.
Yeah. Any other questions?
Actually, I had a question.
Yeah.
I would expect to have full type signatures because you have overloading. So if you have for example, if you have in the random class, you have multiple methods generate with different parameter types.
Yes, then with overloading your handle. Okay, yeah, sure. Then you can, you could say that this is syntax sugar for listing every particular overload, if you will, and then to mention an overload, you put in parentheses all the argument types, I guess. I just kept the formalism simple.
Okay, then let's take the speaker. So, thanks for coming and enjoy your lunch.